My name is Stefan Llewellyn-Smith. I'm the chair of the Department of Mechanical and Aerospace Engineering, and I'd like to welcome you to the Sol Penna lecture, the lecture series given in this winter quarter, the Sol and Beverly Penna Distinguished Lecture. I'll briefly remind people who Sol Penna was. Some people may not know. He was the founding chair of the Ames Department in 1966-65. One can debate that. And that department mutated over the years and has become part of it, the Mechanical and Aerospace Engineering Department, which I'm currently chairing. And today it's a great pleasure to welcome you to listen to our talk today. I'm going to pass over the microphone to Professor Tynan, who was my predecessor, who works in this area. Our speaker is Dean Emeritus. There's a long list of what he does. And I thought I could just say one story. I'm not supposed to, but when I came to UCSD in 1999, Bob was the dean when I was hired. So I came here and I was very young and very naive, and I was terrified of Dean Conn, absolutely terrified. And I got the job, which was good. And then a number of years later, I bumped into Bob on a plane going to Boston. And Bob had left. He said, "How are things, Stefan?" I said, "Oh, I got tenure. It's all great." He said, No. How's the research? How's the exciting stuff?" And so that's what Bob's always interested in, the research, what it's all about, not details and administration. So I'm going to pass it on to Professor Tynan, who will introduce the speaker. Over to you, George.
Thank you, Stefan. And make sure I get the microphone adjusted for my height. So I thought I'd take just a moment to sort of set the stage for today's lecture. If you're paying attention at all, you know that we have a serious issue with climate change, and the solution to climate change requires clean energy. Clean energy is the essential element to that solution. It's also the essential element to lifting the rest of humanity out of energy poverty into a good quality of life. Studies over and over and over again show that the least cost, fastest pathway to a universal carbon-free energy system is to deploy a mix of renewable technologies, solar and wind, along with storage technologies and a certain amount of what we call dispatchable clean energy. That is, sources that we can turn on and off at will. So a hybrid system that combines those technologies is the fastest pathway to a carbon-free energy system. If you go make a list of technologies that could actually scale to meet the demand and also provide dispatchable carbon-free generation, the list is frighteningly short. It's things like we could use fossil fuels but capture the carbon emissions and do something with them. We could store up excess renewable energy and then turn it into hydrogen or what's called synthetic methane or green methane. We could use nuclear power, fission, conventional nuclear power that we have. You could learn how to do deep geothermal technologies, although there's some challenges there, or you have fusion. And that's about it. That's the list. So many of those technologies are being developed now. But the other point for the motivation for today's lecture is if you've also been following the news in the last few years, you will have noticed that the game has changed in fusion energy. There's been an enormous influx of both government funding around the world and now in the last 5-6 years, private sector funding that actually dwarfs the amount of publicly funded research going on. I'm actually pleased to note that one of the key people who made that happen is with us today, Dennis White from MIT. He's here on sabbatical, enjoying a respite from the land of snow and ice. And so fusion is getting people's attention. And so we thought that the Penner lecture today, it would be nice to focus on why. And the speaker today, Bob Conn, is, I would say, extremely well positioned to give us his views on that. Bob spent his early career after his PhD at Caltech as a faculty member first at University of Wisconsin, where he and a colleague there helped establish the subject, at least in this country, for the study of what could a potential fusion reactor look like, given all the constraints that we know from physics and engineering. And Bob really built that field, and that's had a profound shaping effect on the trajectory of fusion research. In the early 90s, he came here to UCSD, the then dean, now Emeritus Dean. And since then has spent his time both in the venture capital world and the world of philanthropy and science. So he knows fusion backwards and forwards. He also knows the larger context in which it sits. And so given these developments, we thought it would be really good to invite him today to share his views on, and as you're going to hear, he was somewhat pessimistic about the possibilities for fusion as a practical energy technology, say 15, 20 years ago. And he, as you're going to hear, his views have shifted. And so without any further ado, I want to invite Bob to the stage. Let's please welcome our speaker today, Bob Conn.
Well, it's great to see a packed room and to see many faces that I recognize, maybe even more faces that I don't, which is a good thing. I also, an old friend of mine from the early 1970s, Steve Dean, runs a group called the Fusion Power Associates. It's really a group of people, 10,000 or so, who do fusion research. And he sent out a Zoom link, this is going to be on Zoom as well, to those people. So I welcome those who are out there on Zoom, in the Zoom world. And my aim today is to talk to you about my views on the prospects of fusion energy. I want to start with a story about Saul Penner, since this is in his honor. Saul and I crossed paths in the ether in 1964. Saul was on the faculty at Caltech and already a very distinguished chemist, chemical engineer, combustion theory, energy, etc. And I was on my way into graduate school. In that same month, and it was 64, Saul left Caltech to come down here at the invitation of the then budding 4-year-old UC San Diego and build an engineering program. Except the state of California, and in particular Berkeley and UCLA, said, we don't need more engineering in California. This is 1964. And so they had to create engineering science programs and applied physics. I think they called the department where Irwin started electrophysics. Couldn't use traditional names. And that's why historically we have funny names. But Saul came down here and he laid the foundation for what we have today. So Saul Penner made a big difference to UC San Diego, and he made a big difference to this school. And I want to acknowledge that. He's passed on, but he was a student of a great physical chemist, Farrington Daniels, at the University of Wisconsin. And I started my career at Wisconsin. So a whole bunch of years later, we crossed paths again in the ether. All right. The big hot question. What is fusion? Where are we going? Let me make sure that this changes, and it does. I've broken the talk up into 5, 6, 7 biteable parts. So you'll see part 1, part 2, part 3. Hopefully each part, just a few slides so that it's absorbable. I hope most of it gets absorbed. If 50% gets taken in, that's wonderful. Anything more is gravy. So let's start with the very basics, since most people here are not nuclear physicists and don't necessarily know anything about nuclear physics. You don't need to. What is fusion energy? What is the fuel? And what are the optimum conditions for burning that fuel? Now, you all know we have stars, right? We've got our star, and there's billions and billions of other stars. What do they burn? Fundamentally, they burn ordinary hydrogen, right? The proton in the middle with the electron that goes around, that's it. And they're so massive that they kind of compress themselves, and the compression sort of heats them up, and they get hot enough that even though ordinary hydrogen burns and fuses very slowly, we got stars, right? So if you've got that kind of gravity, we could use hydrogen. We don't have that kind of gravity, so what do? And it turns out there are some other fuels, basically what we call isotopes of hydrogen, that are the fuels of choice. So what are the isotopes of hydrogen? Well, ordinary hydrogen, everybody knows, it's in water, right? Turns out 1 part in 5,000 in water is heavy water called deuterium. So the deuterium in its nucleus has 1 proton and it has a neutron. So it's twice as heavy, roughly speaking, as hydrogen, but it's stable and you can mine it out of water. The third element is tritium. That's the third isotope of hydrogen. It doesn't occur naturally. It's radioactive. It's one of the weakest radioactivities known to man. It has a 12.5-year half-life, so falls by a factor of 2 in amount in 12.5 years. But it emits an electron, a very low energy electron, when it radioactive decays. That's called a beta particle. Don't worry, beta particle, electron. And it's a very weak radioactivity, but it's radioactive. So we have these two fuels, and it turns out those two fuels react with one another at a rate faster than anything else we know. And so here's a picture of the reaction itself. And what you'll see is on the left is sort of the nomenclature for deuterium and tritium. It has electric charge 1, and then 1 weighs 1 weighs 2. On the right-hand side, you have a neutron, 0 and 1, and a balloon, helium. It comes out as what we call an alpha particle. An alpha particle is nothing more than the nucleus of helium. And it generates about 17.6 million electron volts of energy. I'm going to have to, unfortunately, use electron volts for a measure of energy. 11,000 degrees is 1 eV. So these are 14 million, 17 million eV. It's a lot of energy. 80% of the energy is carried by that neutron. And that's fundamental to fusion, and it's fundamental to how you build machines. And what you do with that neutron is crucial, because it's carrying, again, remember, 80% of the energy. The alpha particle carries 20% of the energy, and we can use that to heat some combination of gaseous mixture of deuterium and tritium and get it up, help get it up and sustain it at fusion temperatures. I didn't mean to do this. Okay. What's the rate at which they react? Well, here's the rate at which they react. The left-hand column is the reaction rate, and the right-hand column is the temperature measured in kilo-electron volts. Essentially, you want to operate where the star is. And the star is about 10, 15 kilovolts, so 10 to 15,000 volts. Hundreds of million degrees, a little bit more, right? You see other fuels that could undergo fusion reactions, nuclear fusion reactions. Deuterium reacts with itself, but at a very much slower rate. Deuterium can react with an isotope of hydrogen, helium-3, also at a very much slower rate. And people have talked about things like protons and boron-11. You may have heard about that. Don't think about it anymore. It's much, much too hard. What are the approaches to achieving practical fusion energy? There's two. One is based on using high-power lasers, football fields of lasers, to hit a tiny pellet about 1 centimeter thick. In fact, even smaller. I mean, if there was ever a sledgehammer hitting a little BB, this is it. And the idea is to compress that BB, which is in fact deuterium and tritium fuel pellet, by a factor of 500 to 1,000 times normal density. Now, everybody knows if you've had a balloon and you just squeeze on it, how it bops out. There are these instabilities. If you don't push uniformly on a sphere, you can't compress it because Kelvin-Helmholtz instabilities, for those who know about it, they jump out and you get instabilities which do not allow you to continue to compress. The fuel breaks out. Uniformity in inertial confinement fusion in the illumination of the target is the key to everything. And they've just had a major achievement. I'll talk about it, but it took 25 years to get that achievement after they started getting the laser to work. So these are not simple tasks. The other approach is to use, now let me be clear, when you get a gas up to temperatures like a kilovolt, 2 kilovolts, 10 kilovolts, 20 kilovolts, the electrons, it's called plasma. It's just the fourth state of matter, solid, liquid, gases. And then gases that get electrified, meaning the electrons and the nuclei are stripped of each other, and positive charges and negative charges are running around. What to do. It's a crazy system. They respond to magnetic fields because it's electrically charged. And we can use magnetic fields in a device such as a tokamak. There are many other devices that one can try. And I will talk about the tokamak, what it is, how it works, why it works. But it's the leading example of how to try to do fusion using magnetic confinement of the plasma, which is getting very hot, right? It's 10 kilovolts. All right. So let's talk about the status of inertial confinement fusion. Inertial confinement fusion means lasers that hit a target, that compress it to the point where, just imagine, so the physical process is not hard to imagine. If you can compress this thing to 500 times solid density, you make shock waves going right to the center of this little pellet. The shock waves, when they dissipate at the center, dissipate and create heat. And if that heat is enough and you do it just right, the temperature will go to 10 or 15 or 20 kilovolts and fusion will begin. Once fusion begins at the middle of this little cold pellet, it propagates out. Why? Because it makes that alpha particle. Remember that 3.5 million volt particle? It has a range that's larger than the central core that just got heated up. And it starts to heat the surrounding fuel. And then that gets hot and starts to have fusion. And the alpha particles propagate out a little further, and you get what's called a propagating burn wave. And it burns through the fuel, and maybe you burn 10 or 20% of the fuel, but that's how laser fusion works. It's big. These are monster machines. This is the building at Lawrence Livermore National Laboratory that houses what's called the National Ignition Facility. It's one of the largest lasers in the world. Operates currently at 2 megajoules of energy, puts the energy out in a few nanoseconds, so 10 to the 14 watts. I mean, wattage that's more than the total wattage put out by the electrical systems in the world, but only for a few nanoseconds. The building is big because it contains the laser, and the laser is enormous. It's a neodymium glass laser, so it lasers at 1.06 microns. That's 1,060 nanometers in terms of the wavelength. And it turns out, if you're illuminating something that's plasma, the coupling of light to the plasma depends on the wavelength and the frequency of the light. You want as high a frequency, as short a wavelength as possible. 1 micron's too long. So what we do is there are these systems, glass systems, that frequency double the frequency. And if you do that twice, you get down to maybe 266 nanometers, 0.26 microns. And that couples very effectively into the plasma. So that's why they do that. Loss of efficiency in the laser, and this laser is 0.1% efficient. So it's not for making energy in the long run, but boy, is it good to illuminate a target and see if the physics works. Got it? So this is really a physics experiment. It's big. This is the target chamber in which, as you'll see, this is 5 to 8 meters in diameter. And at the center of that chamber, all the little holes are for diagnostics for the most part. And a few of them are for letting the laser beams in from one on one side or the other. And it's all trying to hit this fuel. This is a fuel capsule. Notice the dimension, 12 millimeters. It's basically a ½ inch. Okay? So you're trying to get, think of it sideways, turn it 90 degrees. You come in with the lasers from two sides. And at the center of that, what looks like a copper shell, it's called the hole round, sits a target of deuterium and tritium that's spherical. So that's the right-hand piece. And what do we try to do? We illuminate this outside hole round with the laser beams from both sides. There's 192 beams split between the two sides. And they actually don't hit the pellet. They hit the hole round, the cylinder. And they raise its temperature to 300 electron volts. And at that temperature, the hole round radiates. And it radiates uniformly, extremely uniformly. And that gives you the uniform illumination of the pellet to compress it. So there's no more physics to it than that. Technologically, it's an extraordinary challenge. But that's the aim. What happened recently? What's different today from 20 years ago or 10 years ago? Well, in December of 2022, Livermore announced for the first time ever, aside from, it's a university, but I can still use the words, aside from a nuclear weapon, it's the first time we ever produced more energy out using fusion than we put energy into the system to make it fuse. That's nirvana when it comes to the physics of fusion. So you see what the capsule was, and if I have a pointer here, how do I make this pointer work? There we go. If you look at the pulse, this is the laser pulse on the target. It lasts for about 4 or 5 nanoseconds. Here's the peak power. And if you look here, they measure the temperature of this sidewalls of the hole round. And it gets up to about 300 electron volts. And that radiation illuminates this target of DT gas. It's got a cryogenic shell around it. And what they got was more energy out than in for the first time in history. So they put about 1.5 million joules of energy on this target for 4 or 5 nanoseconds, and they got back out 1.5 times what they put in. So that means they got the fuel to ignite, the middle went off, and then it propagated out with the alpha particles. A heroic achievement. This has been both magnetic and laser fusion, I got to tell you, are Sisyphean efforts. I've been in the business since 1970. I didn't do it for my doctoral degree, as George said. I learned it when I went to Wisconsin and they had a program in this area. I've been at it 55 years. We're still at it. It's a tough pull. Nonetheless, this is magical. And so what's next for inertial confinement fusion? Well, they're going to continue to raise the energy of this laser. I'm confident that they will get gains. The gain scales what we call non-linearly with the energy on the target. So if you double the energy, you might get 100 times more out than you put in. And they may get up to a gain of 100. I think this is highly likely in the next 5 years. But I would point out, for the first time in laser fusion, we're not alone in the world. China is building an even larger laser, and they hope to have it up and operating within the coming decade. So there'll be some competition, no question about it. Now, those topics are supported by the government, but they're supported by a part of the Department of Energy called the National Nuclear Security Administration. And the purpose of this program, again, don't throw me out of the room, I'm just speaking. The purpose of this program is to help us understand our nuclear weapon stockpile. We have nuclear weapons, Russia has nuclear weapons, China has nuclear weapons, others have nuclear weapons. Will they work if they ever have to be used? You dearly hope you never have to use them. But if you do, would it work? You have to continuously monitor your stockpile to ensure you're going to work, and you have to be able to calculate things. This is related to how a weapon works, at least a small piece of how a weapon works, and so they support it. But to make energy, which is not the objective of this program, you need a reparatable laser with 15 or 20% efficiency. We shoot the laser at Livermore once, at most twice a day. It's got a 1/10% efficiency. We need 100 times the efficiency, and we need even more than that by the way of the rep rate. We need at least once a second, maybe 10 times a second, if you want to make energy. So this is a long way from making energy, but the principles of how you could go about doing it from a physics point of view have now been established. There are many other areas that are important to work on. The reparatable laser, I said. And there's the whole rest of the system you would need to build around this target that's going off maybe 1 to 5 times a second to capture the neutron energy, capture the blast energy, and find a practical way to convert it into electricity. No mean trick. What's the status? That's the status of inertial confinement fusion. So a great achievement, long way to go. Personal view. What's the status of magnetic confinement fusion? Well, magnetic confinement has a longer history just because the laser wasn't invented until 1960. But figuring out that you could use magnetic fields to contain a hot plasma was understood ages ago. And after the war, we began programs. The Soviet Union began a program. The US had a program. The most successful of all these approaches has been something called the tokamak, a Russian invention of 3 very famous Russian physicists. Andrei Sakharov, everybody knows because he also won the Peace Prize. But Igor Tamm won the prize in physics, and Lev Atsimovich was one of the leading plasma physicists of the old Soviet Union. They built this machine, and when fusion energy was declassified and made public in 1958 at an Atoms for Peace conference, they showed that picture. 10 years later, in another version of this called T3, that was T1, they got a plasma with 300 electron volts at the center. Stunning. Nobody believed it. In one of the breakthroughs of the Cold War, they allowed the British to bring a laser to the Kurchatov Institute in Moscow and put it on this machine and use Thomson scattering. Don't worry about the words. Use Thomson scattering, it's a scattering off fluctuations of the electrons, to measure the electron temperature. We did not believe the way the Russians measured it because it had to do with the resistance of the current flowing in the plasma. The world changed. Everybody shifted to working on a tokamak after the results of T3. What is it? If I could wave my arms a little bit, I hope I can make it at least minimally understandable to you. This is the center of the chamber. See that little circle? That's supposed to represent the center of the plasma. Think of a donut. It's just a donut. all right, of a certain physical size, except it's not made of cream and flour and so on. It's positive ions and electrons in something we call plasma. How do you make it work? Well, you see this big iron leg. Think of the plasma that carries a current here as the secondary of a one-turn transformer. So in your electrical engineering courses at the undergraduate level, you learn about transformers. Well, this is nothing more than a transformer. You put primary windings in, you run the current up linearly with time, it generates an electric field around the torus. That electric field drives a current. The current makes a magnetic field, use the right-hand rule, and the magnetic field lines then twist as they go around the plasma. They don't twist too fast. Have to go around 3 times for the head to catch the tail. But that's the principle in which you can contain a plasma in a tokamak. Take it from me, it works, and we've been doing it for more than 50 years. This is a young fellow. I have no idea who this guy is. He must be in his early 30s. He's got a mustache. He still has hair. And he's standing in Moscow in the leading Russian lab at the time called the Kurchatov Institute, still a leading Russian physics laboratory, next to the next version of the tokamak machine called T10. So this is bigger than T1, bigger than T3. It's big. And you can get a sense for it by, I'm still about 6 feet. So you can get a sense of the scale of the machine. Everything is on the inside and covered up except for the iron core of the transformer. And that's about all you really see in this. But it was interesting. At that point in 1975, we were taking data with computers. The Russians were still printing out the data from the diagnostics they had on this device on paper tape. That's a measure of the difference. Well, since then, we've built an extraordinary number of these tokamak machines. The most productive by far, I think, in the world was the Joint European Torus device called JET. It operated for 40 years, and it really illuminated a whole panoply of physics issues when it comes to understanding how a plasma operates. There were other machines in the world. At MIT, they had the Alcator machines, many other devices. But I would say this was the biggest and sort of the best. Today, the biggest machine is this superconducting machine. That is, you make a toroidal magnetic field around the donut. You do that with magnets that go around the donut, this way, this way, this way. And they have a D shape. Another question. Inside this vessel are 12 to 16 D-shaped superconducting magnets that make the main toroidal field of about 4, 5, 6 Tesla. Maybe a little less. And this machine here on the right goes back to the Gorbachev summit with Ronald Reagan. In 1985, they proposed to do a joint project together between the old Soviet Union and the United States. And it became what today is called the ITER project, International Thermonuclear Experimental Reactor. That's what the 3-word letters stand for. We're still building it. I was on the first technical advisory committee overseeing the whole program with a Russian, a person from Japan, and a person from Europe. We wrote a paper about ITER in Scientific American, the first public publication of the ITER project. Guess the year, 1992. We're still at it. It's still not working. But it's an international project. It's cost $20 billion. It's being built in the center of France with support from the United States, Japan. Russia had been supporting it. Obviously, Europe and other countries have joined as well. I'll have more to say about that. But here's a great machine that's just off campus. This is the D3D, called D3D because it looks like a D and it's the third one. And it's at General Atomics, just on the mesa, just north of campus. Gives you a nice idea of what these things look like conceptually. Here's a center post with tiles on it, you know, like a satellite coming back in. We got to have tiles to take the heat and so on and so forth. This is the main plasma. It has a sort of a D shape. This is the plasma boundary layer. That's the plasma edge where the heat and particles are carried down here to some plates that absorb that heat and take it away. It's been an extraordinarily productive device. And we at UC San Diego have been doing experiments on that device since I came down here in 1994. So what is that? It's a long time, 31. And we've been doing experiments at D3D, led by UC San Diego, doing experiments on that device. It's been terrific. So what's different today? One thing about the tokamaks is they've been very, very complicated, very hard to understand. You think fluid mechanics, those of you in mechanical aerospace engineering, you know, you got an ordinary fluid, water flowing in a pipe, straightforward, right? Figured out a lot of that in the 19th century, a lot more now. Turbulence is really hard. It's an ordinary liquid. Now start with something that's a bunch of charged particles running around in any direction they like, except that we're making them follow these magnetic field lines. Predicting the performance of that kind of a device and the turbulence in it is heroic. And yet, George Tynan, who introduced me, has spent a good 25 years trying to figure this out. And about 10 years ago, he hit the button. And to make it simple, and I borrowed these from George, this is the pressure profile. Think of the donut, and all I'm doing is plotting the pressure across the radius of the donut. Not this way, just the radius of the donut. And you see it peaks in the middle and goes down towards the edge. Well, that you'd expect. There's a velocity profile. So this plasma, just to make you, this plasma is rotating. But it's not rotating like a log. A log would rotate, right? The velocity would be linear with the radius. No, this is rotating and it's sheared. The velocity on the outside of the device is faster than the layer next to it, and it's tearing at each other. That's called shear flow. And what happens in these devices, and I credit George a lot with this, but others too, of course. This has been a big, big field of research. What happens is these vortices form and try to carry the heat and mass out, just like in turbulence. Except what happens is that this original layer, these vortices energize it and it peaks way up. And the shearing becomes extraordinarily large. And so as these vortices get towards this high shear zone, they tear apart. They can't stand up to the vortex. And I called it with George the shear layer where vortices go to die. But conceptually, what it means is inside this peak layer, the heat and the particles are well confined. And you can get to high temperature. And that's a physics breakthrough of the first order. Thank you, George. Here is an example of a device where this is going on. It's in China. And you can see that they've run this device for 1,000 seconds. Now, if they had the capability, they could have run it forever. All they're showing is we can run steady state. So we can make a tokamak and we can make it run steady state. And if you look here, I only care about this line for the purposes of the talk. The temperature is about 7 kilovolts. And the ion temperature is actually hotter. Remember the number we needed for fusion. Ion temperature is 10 kilovolts or more. So while this is an ordinary hydrogen or deuterium plasma, it's got all the parameters needed for fusion energy. This is the most exciting part, aside from the physics. I'm a physicist, so I love George's work. But the other piece, where I spent a lot of time in my career, occurred with a postdoc of mine, Dennis White, who was here late 90s, early 2000s, went on to Wisconsin, went on from Wisconsin smartly, by MIT was smart, smartly back to MIT. And recently he's been the director of their fusion program at MIT. He just stepped down. So I feel like I didn't do any of this, except have a great student in George Tynan and a great postdoc in Dennis White. That's how fields propagate. What they did is they tried to think outside the box. How could I make the magnetic field even higher than anything we've ever done? The maximum field we've ever made at the edge of the coil is maybe 8 or 10 Tesla. Tesla is a measure of the magnetic field. It's 10,000 Gauss. The Earth's magnetic field is half a Gauss. So 10 Tesla, you can do the math, right? And if I get to 20 Tesla, 200,000 Gauss, well, that's twice the field. Everything in magnetic fusion, roughly speaking, scales at the square of the magnetic field. So you make the magnetic field twice as large, you can make the device a fourth the size. You can make this better, you can make that better, and so on. And Dennis challenged his students to come up with an idea for designing a device of this kind. This was maybe a decade ago. And they ended up working and developing a high temperature superconducting wire. They're called rare earth barium copper oxides. The rare earth in this case is yttrium. And they built a coil, they tested it, and it ran up. If you can't see it, this is 20 Tesla. And these are time in hours. So they got the coil up to 20 Tesla and they held it there for hours. Proof of principle of something that we thought was impossible. And I think that is heroic as an achievement, as important as the physics gains that we have had. The other thing they did, and this for me doing fusion engineering in the 1970s, I could not imagine taking a superconducting coil apart. I mean, forget it. You have something operating at 3 degrees absolute. It's got windings going inside that coil. You're going to make a joint in this? Give me a break. Well, they said maybe we could make a joint in a superconducting coil. And they designed one. This is the outer leg of the coil. When they put it together, they got a D-shaped magnet. This is what the joint looks like, and it's very low loss. That's an experimental result. So they have established the practicality of making a joint in a magnet. And to me, when Dennis told me about this, I just went, holy mackerel, this is a game changer. Not only the high temperature superconductor, but the ability ultimately to take the magnet apart, because it makes maintenance of the device dramatically more easy. And that's the implications of the joint. What else is different today? Well, George hinted at it. Private support for fusion energy. There's a company that Dennis spun out of MIT called Commonwealth Fusion Energy. It's raised $2 billion of private money. It's raised it from these people. So this is Vinod Khosla, one of the most successful venture capitalists ever, founder of Sun Microsystems. This is Peter Thiel, Jeff Bezos of Amazon fame, obviously Bill Gates, and Mark Benioff in the middle, who founded Salesforce. That's where the bulk of the money came from. That's amazing. They spent 15 months doing due diligence on these coils with 3 separate groups before concluding we're ready to invest. And these are enormous bets. $2 billion, even if spread over 10 investors, is still $200 million per investor. It's a lot of money. And you better make a big hit to return those funds. But nonetheless, that's a big change in the business. And this spin out that I mentioned from MIT called Commonwealth Fusion Systems is now has designed and is now building a tokamak machine that's rather compact. The field on the axis of the device is 12 Tesla. So that means it's 18 to 20 Tesla at the coil, because the magnetic field falls as 1 over the major radius in the torus. So you don't get the field at the middle of the device that you get at the coil. You get something lower. But that's still 2 to 2.5 times higher than anybody else has ever gotten. So this is a heroic device. And what it means is the device is relatively small. The major radius from the center line of this device to the center of this plasma is under 2 meters. That's a compact machine, folks. And they hope to build it and get it running by 2027, 2028. If they do, they'll put deuterium and tritium in it at some point after learning how to run the machine, which might take them a few years. And if they put deuterium and tritium into this device, my conclusion is the following. So this is an assessment after decades and decades of working in this business. I've got high confidence that if they can make the machine work, where they've got proof of principle, but they haven't made all these coils work themselves in a torus, in a real tokamak machine. But if they can make it work, they will get high heat and particle confinement. They will get ignition of the fuel and burn and steady burn. And that steady burn will be driven for a reasonable amount of time. That's nirvana for tokamak magnetic fusion energy. It's the same achievement as has happened with laser fusion. What's different is I think that there's follow-ons to these devices that are more practical than otherwise. This is a big machine. That's that ITER machine I talked to you about. Notice the person here. That's a 6-foot person. If I go back, that's the same 6-foot person. So it gives you a sense of the scale reduction that's occurred because of the magnetic field. So what's coming? Well, the Commonwealth Fusion people have in mind a demonstration reactor to follow the spark device. This all may be a little too quick, but they're ambitious. And they've got private support, so they better deliver. And so they have a design for a demonstration power reactor. The ITER machine will eventually work. Currently, it's scheduled to start operating in 2035. But it's not going to do deuterium and tritium plasmas until 2040, 15 years from now. This has got to beat them. We need it to beat them. It's not that I wish anything bad on my friends in the ITER program, but we've got to go faster. And so they both plan DT operation by 2040. It's supposed to go backwards. So here's a comparison of these two devices. Don't worry about the graph. They're both trying to do the same thing, make 500 megawatts thermal of fusion power. And you can see the scale difference. I don't need to say anything more, right? If you weigh the upper guy, you'll never have an economic system, never. But if you weigh the lower guy, you got a shot. And that's the essence of it. So I'm optimistic that if they can make these spark machines work, they can get to ARC and have a practical approach to fusion energy. Now I'm going to end on a cautionary note. I mentioned in the beginning that deuterium and tritium makes a neutron and helium. The neutron's not confined by plasma. It doesn't know from beans about plasmas. It needs to run into something solid, which is the surrounding materials. And a 14 MeV neutron has a mean distance to its first collision of about an inch, 2.5 centimeters. If you want to knock that energy down by a factor of 1,000,000, you better have about 25, 30, 40 centimeters worth of material around. That's fundamental physics. You cannot avoid it. So what happens, and again, somebody made these go like that. This is from work of myself and my group back in the 1970s to show you how far back we first came to understand the issues associated with trying to achieve practical fusion energy. And what you're looking at here is fusion machines in terms of the waste disposal and what you do with the materials. They're what you eat. They're a function of what you build them out of. So if you build a machine out of stainless steel, that's this dashed line here. It takes about 1,000 years for the radioactivity that's induced by the neutrons hitting the iron, nickel, and chrome in the steel to cool down by a factor of 1,000,000. If you could figure out how to do it with carbon or silicon carbide, you get this dashed line, which is way down. In 10 years, it's down by a factor of 1,000,000. So materials development with low atomic number materials like silicon and carbon are what you need to make it environmentally friendly. We don't exactly know how to do that, but that's the challenge UC San Diego should pick up. Frankly, MIT should too, except they got a lot on their plate. So that's just the caution, right? This is not without radioactivity. It does depend a lot on what you build it out of. So put a lot of energy into what you build it out of so you don't get a lot of radioactivity. I'll close with this. I think we'll see ignition and sustained burn in a tokamak device in the next decade. I'm confident in the laser fusion area you're going to get gains up to 100 in the next 5 years, maybe sooner. And I'm pretty confident that you'll see within 15 years the design and construction of a demonstration fusion power device, most likely based on the tokamak. Thank you very much. Okay. We made it, right? We got time for questions. Any questions? David.
So Bob, tell us, ITER is consuming vast amounts of capital. Why should that project continue given all the other innovations that
Well, first of all all the other innovations that I talked about applied to the spark device of Commonwealth fusion. So you should be putting the money there. There's money going into a wide variety of other approaches. There's a company called Excimer building a krypton fluoride excimer laser to try to do laser fusion. There are other companies trying other magnetic confinement approaches. The approach where we know the physics is the tokamak. Everything else, you're betting on the come. You don't really know the fundamentals. Field reverse configurations, you name it. And so I don't have nearly as much confidence as I have in those other startups than I have in Commonwealth fusion. Just because we've proved, in principle, we've proved the engineering they want to do, and we know the physics. And those are hard things to come by. It's taken 75 years to get there. Ken.
You mentioned that part of the material requirement is silicon carbide. Obviously, silicon carbide has been around forever, and we know that General Atomics has been building silicon carbide enclosure materials for this purpose for a long time. So what is the problem with existing silicon carbide technology?
So I advise you to talk to your colleague, Mark Tilak, who is here. Mark, raise your hand so people know who you are. Mark and I first met when he was an undergraduate in 1975 at the University of Wisconsin. And he ended up coming down from UCLA to UC San Diego when I moved. He knows more about this than I do. I'd put it more generally, Ken. I would say you want to find some combination of materials of low atomic weight, because low atomic weight materials don't induce a lot of neutron radioactivity. So it's the low atomic weight that's crucial. Silicon carbide is a candidate, and it comes in many forms, and I'm not enough of a material scientist to tell you why that might work better than something else. But we need an invention. Charles?
So you emphasize in tomahawk, but laser fusion, has achieved gain. So isn't that sort of farther ahead and has more future?
Well, it depends on what you're measuring, Charles. So if you're measuring distance to a practical fusion energy device, it's not ahead. But if you measure just performance, say by ignition and burn, then it is ahead. I don't think it's so far ahead because we haven't built a magnetic confinement device to do what they've took 20 years to do in laser fusion. But I think we understand the physics so well now in a tokamak area that that's a foregone conclusion. That's my conclusion. So I bet on that. Then I ask myself, what's the rest of the system? And when I look at what the rest of the system is, I think the tokamak has a leg up. But, there are people who have other opinions, and who knows? This has been a long game, right? We're playing a long game.
Thank you.
Shaya.
Hi, Bob. A quick question. Time. You mentioned in laser fusion nanoseconds pulses. What if I make much, much shorter pulses with much higher peak power? Would that have any impact on the laser fusion? Or energy is the only thing counts?
It would work so long as you could get the uniformity and get the power. The power is really the key here. So you got to build a laser that's generating megajoules of energy. If you got a laser that generates megajoules of energy, go for it.
If I squeeze it into a few femtoseconds, my peak power is gigantic.
Yes, that's true, but I think it might not be enough to compress the target in that time. You need a certain combination of length of energy on target and the intensity on target. And that combination is about what you need. So you can raise the intensity on target, but then you better have the rest of the equation fit. The krypton fluoride people are trying to do 10 megajoule lasers. These are excimer lasers, and they want to put 10 megajoules on the target and build a big target and make it work. So, Shaya, the problem is the following. Beam quality. Beam quality. So you're a laser guy, you know what I'm talking about. So part of the problem with krypton fluoride has been the quality of the beam. If it's not really super duper uniform across the beam cross section, you make instabilities when the laser hits the inside of the target. It makes the inside of the hole round non-uniform. So therefore it radiates non-uniformly on the target. Therefore it doesn't compress the target properly. Maybe one last one. Anybody got a last question?
Yeah, I have a last question. We all agree that companies are not going to be able to have net power to sell for of this kind for more than 10 years. So what motivates the private capital?
Well, you'd have to, frankly, ask the people putting in the private capital. But I did do venture capital for 6 years. That is, I was a partner in a venture capital firm, and I made investment bets on technology companies. One of the differences now compared to when I was doing that in the 2000s is the amount of money available to these funds. Some of these funds are $5 billion funds. So think about it. You put up $100 million, it's a small fraction of $5 billion. So a number of these firms take the attitude, I'm going to make a crazy, crazy bet with not more than 10% of the total capital in my fund. But when they've got a fund that's $5 billion, 10% is 500 million. So they're working with much larger funds than was true of venture capital in the 1980s and 90s. I mean, when I was doing venture capital, the firm had a fund, the biggest fund was 350 million. These guys have 10 times that. So it's that I'll take a maximal risk with a certain fraction of the funds available to me. And that's the attitude. That's the explanation. Okay, the funds are very large. The venture capital fund, individual funds, are very large these days. Well, thank you again very much for your attention.